Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. Good morning, good afternoon, and good evening. Welcome, everyone, to today's session on modeling population dynamics with AI. It's going to be a hands-on workshop with the Population Dynamics Foundation model. My name is Rohini. I work with the Climate and Environment Data Unit at UNICEF, also a GeoAI enthusiast, and it's an absolute honor for me to introduce a new episode in the GeoAI Discovery Series. We launched the series back in 2022, and we discussed a variety of GeoAI applications, policies, ethics, what the future of GeoAI for good looks like, with many thematic sessions, including climate action, spatial digital twins, energy, ecology, agriculture, water, and a diverse range of topics. Current focus of the series has been on geospatial large language models, and in the organization of hands-on workshops focused on building practical skills and applying AI to geospatial data under the leadership of the curator of the series, Dr. Maria Bravelli. If you missed some episodes, don't worry, you can watch the recordings of these events on YouTube or on our neural network to which you are connected right now. Without further ado, let me introduce Dr. Maria Bravelli, who will moderate today's event. Maria is a professor of GIS at the Politecnico di Milano, at Geoinformatics Engineering course of study, and also a member of the Schools of Doctoral Studies in Data Science and Earth Observation at Roma La Sapienza. Amongst many, many activities that she is involved in, she is also the Vice President of the Commission of Geospatial Information of ISPRS, member of the board of the UN GGIM Academic Network, and co-chair of the UN OpenGIS Initiative. It's an absolute pleasure for me to introduce Dr. Maria, and over to her to introduce all of our excellent speakers for the day.
Thank you. Thank you so much, Rohini, for this kind introduction, and good afternoon, good morning, good evening to everyone also on my side. I'm very happy to have the second event here where we are hosting Dr. Qiushen Wu, who is an associate professor and the director of the graduate studies in the Department of Geography and Sustainability at the University of Tennessee, Knoxville. And he also serves as an Amazon visiting academic. He specializes in geospatial data science and open source software development, with a research focusing on utilizing big geospatial data and cloud computing to study environmental changes, particularly in surface water and wetland inundation dynamics. He's the creator of many widely used open source Python packages, including GMap, LeafMap, and Segment Geospatial, which are designed for advanced geospatial analysis and visualization. But you can explore more his open source contribution on GitHub, searching in github.com OpenGeos. And then we have two other guests today. The first one is Dr. David Schottlander, who is a senior product manager in Google Research, working on geospatial AI, and is a contributor to the release of the Population Dynamic Foundation model Embeddings last year. His current research interests are modeling the impact of climate events on population dynamics and the application of generative AI to accelerating geospatial data science. Previously, he spent 2 decades working at the intersection of health informatics, diagnostic imaging, and AI, and he has a PhD from the Oxford University in medical image reconstruction. The second guest is Dr. Gautam Prasad, who is a software engineer in Google Research, working on geospatial machine learning, including the population dynamic foundation model, and other work related to extreme heat. His focus is to address health, socioeconomic, and environmental-related problems using innovative techniques that leverage unique data sources. Previously, Dr. Prasad worked on human-related computer vision, including emotion recognition, eye tracking, and gesture recognition. Prior to Google, he studied brain connectivity patterns in health and disease using magnetic resonance imaging machine learning. So very welcome to all of you. And now I hand it over to you, Rohini, for introducing the topic of today.
Thank you, Maria. I know all of our participants are excited and waiting for this second in the series this month. Today, we'll be hearing about the transformative potential of the Population Dynamics Foundation Model, or PDFM. This is a cutting-edge AI model designed to capture complex, multidimensional interactions among human behaviors, environmental factors, and local contexts. So before we jump into the exciting hands-on sections, we'll be getting an in-depth introduction into these embeddings and their applications in geospatial analysis, public health, socioeconomic modeling from all our speakers. To begin with, I would like to call on David to hear more about the history behind PDF. David, please walk us through on how all of this got started.
Okay, hi everyone. Okay. Should I start my video? My video is not working. Are my slides showing?
Yes, go ahead, David. We can hear you.
Okay, great. Thank you so much to the ITU for inviting us, and Kisheng. Thrilled to be helping you sort of with this workshop. My name is David from Google Research, as mentioned, and I wanted to just give a little bit of backstory about the work here on population dynamics, or PDFM for short, because who doesn't love a good acronym? And I'll keep it short because we want to get into the code and sort of start getting hands-on. Just sort of 1 minute on Google Research. We're obviously part of Google, and our mission is really to ask the big questions and then try to answer them. So we have folk making really big advances in a huge range of things, all the way from quantum computing to ML efficiency. Like we have a Coral AI TPU, and then a huge range of things in climate modeling, breakthroughs in AI-based atmospheric modeling like neural GCM and fire and flood models. So let me sort of just talk a little bit about the background here. So we at Google obviously have a bit of a thing for data. We're swimming in data. There's over 100 billion searches happening every month, and we really get this front row seat to sort of the world's curiosities and anxieties and everything in between. And the sort of most interesting part of that is that 15 to 20% of searches are really totally new things that we just have never seen before. So it's like the world's largest, most honest focus group. It sort of reveals things that people might not even share with their therapists, or maybe they do, who knows. There's this book by Seth Stevens-Davidowitz, which is actually a really good read about it. And he sort of describes Google searches as the digital truth serum. And it's actually fascinating when you start looking at some of the things that search trends can tell you. And I think we sort of all know that. So we had some scientists, actually the chief economist in Google called Hal Varian, quite a long time ago now, 13 years back, was sort of looking at, well, beyond the human interest, like, can we actually do something useful with Google Trends? And they sort of wrote this first paper looking at actually trying to predict economic values. They called it predicting the present. And it actually worked really well, and the paper has been very popular. Probably many people here know it. It's been cited a lot of times, and it really showed the value of using the data in this way. And rolling forward, sort of fast forward to today, you can access Google Trends in trends.google.com, and you can also access some of the information that we have about maps, and busyness and things like that. There's a set of cloud APIs that gives sort of access to some of that sort of data. But we sort of felt that it's not that easy to really use this information for machine learning. And so what we set out to do with population dynamics, with this foundation model, was try and distill this wide range of data down into sets of sort of geospatial signatures. And so what I'm sort of illustrating in this slide is just one example use case, where in the middle you've got sort of got this distillation of the data. And in this particular example, we're using it as a sort of pre-trained model to help do super resolution on a metric like social vulnerability index, which may not be available at the sort of high resolution level that you want for your analysis. So this data becomes a useful sort of input signal to it. And so that was really the question and the motivation for population dynamics, was how can we make all of this data ML friendly for geospatial analysis, and this is sort of the result. So let me hand you over to Gautam, who can sort of talk at a much more technical level about what we've done, and we'll be thrilled to sort of be part of the workshop today and sort of help answer questions and see what sorts of things you're curious about.
Thanks, David, and thanks for inviting us to help out with this workshop. I can go through a summary of the population dynamics foundation model, and a lot of the motivation here is being able to access these really rich data sets that cover the environment and human behavior and thought, and encapsulate them into a compact representation that you can take and use for your own modeling purposes. And to summarize, all of the data that goes into this foundation model come from 5 different data sets. This includes aggregated search trends, where we've gone through things at the zip code level in the US right now and extracted the top 1,000 search queries. And these are all aggregated at the zip code over a month-long period. We also look at maps, which is a summary of the different types of places in a zip code or a county region, which could be restaurants or bookstores or hospitals. And they're all aggregated, again, at these large spatial scales. And we give a histogram of this type of frequency. We also include busyness, which is a measure of the number of placement visits at each of these categories for maps, and a bunch of metrics related to weather and air quality. And one interesting thing about all of these data sources is the search and the weather and the air quality are from 2022, while the maps and the busyness are from 2024. And there is some temporal misalignment, but as you can see, that actually works really surprisingly well in practice as we're trying to model things, and this representation we have is pretty stable. The way we use this foundation model right now is we evaluate on a bunch of geospatial tasks. This includes interpolation, extrapolation, super resolution, and forecasting. And the way that this is applied is our foundation model produces embeddings, or you can think of these as features, at specific administrative regions. And then we train a downstream model on top of these embeddings and some kind of ground truth data to actually predict something in practice. Next slide. Thanks. This is an overview of how we take that data and actually build an embedding. And we do this using a graph neural network. The graph representation will take a county or a zip code and represent that as a node. And then the relationship between nodes is represented as the distance between, let's say, 2 zip codes or a county and a zip code, and the spatial or the affinity between those nodes based on something like the correlation between search data. And we rely on GraphSage, and we build a neural network on top of this graph representation, and we map all of this data into a specific embedding that is around 300 in length, where there's select portions that we've optimized for search, maps and busyness, and weather and air quality. And the output of this graph is what we have released publicly. Next slide. Google also released this amazing foundation model from another team to forecast events, and it's a general purpose time series model called times FM. And this is an example for how we can showcase how to apply these embeddings from population dynamics foundation model to a separate model to try to predict something. Next slide. And this is a breakdown for how that works. We can take something like poverty and look at those time series over time across the US. And you can feed that into times FM and make a prediction for the future. So you could say, like, predict the rate of poverty from 2010 to 2020 based on learnings from 2000 to 2010. And what we've done is train an adapter model where for each of these zip codes, let's say across the US, we can create a small neural network that tries to predict the error between the times FM prediction and the ground truth. And that's what we do in the training time. And then in inference time, we can run times FM to predict poverty and try to use this adapter network in combination with the embeddings to try to fix that error. Next slide. And we've tested population dynamics foundation model on a bunch of different categories to evaluate its performance. This is across health, socioeconomic, and environmental variables, and each of these target variables is available at the zip code and the county level. And we can do interesting things like interpolation, where we have select zip codes removed, extrapolation, where we could remove entire states and try to fill in those gaps, super resolution, where we can take data that is only, like, we can contrive an example where it's only available at the county level and try to predict the zip code level. And in some cases, when there's temporal data, we can feed it into this times FM setup and try to forecast with it. Next slide.
Is the screen frozen? Or is it David cannot hear us?
I can try to present the last slide.
Yeah, it looks like David lost the connection.
Okay, I can try. Okay, there's only one more slide left, but here's an overview of the comparison of a model trained using PDFM versus a bunch of individual modalities we use to build the embedding, and also some other widely available foundation models for geospatial analysis, including SatClip and GeoClip, which is a representation of satellite data and personal photography data, geolocalized and learned in a model. And you can see for interpolation, the model does really well by being able to generalize a bunch of these 3 different categories of target variables. And then for extrapolation and super resolution, you can see the breakdown of different modalities and the comparison with SatClip and GeoClip. We also, on the bottom right, give an overview of how we do with forecasting. And in particular, we studied unemployment rate at the county level and poverty rate at the postal code level, and compared the base times FM model, the foundation model, with a fully supervised approach called ARIMA, and a model where we've taken times FM, trained an adapter, and used that with the embeddings, and we show we can improve some results there. And we're hoping that people can take these embeddings, use them for their own creative purposes and use cases, and can gain a lot of value from the modeling capabilities here. And that's all I had.
Thank you so much, David and Gautam. This is quite inspiring, and I can already ask a lot of questions, but I will wait until the end. So I also ask all of our audience today to put any questions they might have on the chat. Now over to the most exciting part, and Dr. Kingshabu, we are looking forward to hearing from you.
Okay, let me share my screen here. Okay, thanks for joining, and thank you, David and Gautam, for the introduction, and also the introducing the PDFM framework. And so for me, we are going to get to introduce you the hands-on how to get started with using the model. As you can see from the introduction, the PDFM is quite powerful. You can do a lot of things, especially things related to human behavior. Once you have the embedding, you can do a lot of prediction, super resolution. For today, we're going to just get into the basic. We don't have enough time to get into all the use cases, but hopefully it will give you some flavor, and then you have this sample calls. You're welcome to adapt to your own data. One thing to keep in mind is right now the embedding is only available at the US county level and also the zip code level. Right now, for outside the US, we don't have the embedding yet for other countries, but hopefully in the future, they may release other embeddings if there's enough use cases, and I don't know. So, but I want to introduce you how to use it. It's very powerful, and it's very easy to get started. You don't need super complicated deep learning knowledge. You can just use some basic machine learning, linear regression, for example, and then you'll be able to build a model, and then you can do prediction. You can do interpolation. You can also do super resolution. So the notebook example is available at GeoAI tutorial.gshub.org, and then on the left side there's a link here. Go to the AI for Good 2025. I will send the link in the chat here. So notebook. You can access this one freely. So once you're on the page, here you can right click and open in Google Colab. You don't need to install things on computer. We can just use Google Colab to follow these notebooks. Make sure you log into your account. Upper right corner here, if you have not logged in, you can log into your account using your Google account. And after that, you can just scroll down here. And I would like to introduce you here. You can find the PDFM GitHub repository. If you click the link, it should take you to the GitHub repository. So this is where they host the source code. You can read more information about the PDFM here on this page. You can also read the paper if you want technical, more technical details about the paper, how it was changed, and also the framework of the model. And you do need to get access to the embeddings to submit the Google form. You can use this one. I think it's easier to get approval. So in the prerequisite section here, click the access to PDFM embeddings. Open this one in a new tab. From here, just need to enter your email and then just a brief description about how you're going to use it. And then after you submit, you should receive an email. And in the email, there should be a link to download the PDFM embeddings. So it's a zip file. Once you download it to computer, it's going to look like this: PDFM embedding.zip file, and you can just unzip that on your computer using whatever software that you use. Inside, you'll be able to find the embeddings. So V0 US, you should be able to see 4 files. So let me zoom in a little bit here. Country.geojson, GCTA, so zip codes, census tabulation area. So this is just for the US. And we have 2 CSV files. So these 2 CSV files, basically, one is the embedding for US county level. The other one is the embedding for zip code level. If you want to open it, you can try it, but we're going to use Python to read it. If you can see the file, it's actually the CSV is pretty big. So maybe let me open the county just to show you what it looks like. Think about this is just the weight of the model. So if you open the file, let me maybe zoom in a little bit here, so you can see what the model looks like. Of course, you need to get access to the embeddings. So we're just going to show you what's inside. So for the county level, you're going to see there's a column called place, and then there's a geo ID, also the 5-digit. So the 5 digits basically represent the county ID. So the first 2 digits are the state. The other 3 digits are the county. So within the county within a state. So each basically unique ID represent one county. So for example, Alabama is 01, and then 001 is basically this county. So if you scroll down in this file, you can find 3,088 counties. So basically all the US counties in the US, and also you can see some basic information, the county, the population, latitude, and longitude. So these are the basic information, and after that, you'll be the so-called embedding, so features, different features. And these are just the weight. And if you scroll all the way to the right, in total, we have 330 features. So starting from 0 to 329, and each feature basically one column. So you can think about this as just the weight. And then we can use this one to build a model to do prediction on whatever socioeconomic factors that you want to predict. So we're going to get hands-on on that later. But this is basically what the embedding looks like. It's just numerical representations capture the spatial relationship between those counties. And although we don't know what each feature represents, it's just something, just like you're using some large language models, like it's just the weight. And then once you feed in the data, it's going to go through the some multiplication, manipulation with the weight, and then give you the outputs. And this essentially it is what it is. So this is for the county level. There's also the zip code level, but this one is much larger. So it's 110 megabyte. It's the same number of features. So it's also 330 features, but the number of zip codes is a lot larger. So it's with 33,000. So if you open it, don't try to open it on your computer. It's probably too big. It might freeze your computer. But if you want, you can certainly open and then take a look at what's inside. Again, we are going to use Python to read the file. And okay, it's all open. So let me go to the end. All right. So here 32,070. So basically 32,069 because the first one is the header. So it's like 10 times more than the county level. So this is lots of data. But in terms of the feature, it's the same. So it's 330. So I can scroll to the right here just that you take a look at what it looks like. Anyway, so let's get hands-on how to utilize these embeddings to do some simple analysis with housing price. Okay, so once you open the notebook, then we can get started. If you want to study out on a local computer, you can also use this command line. So if you're familiar with Conda, you can install it yourself. But just for simplicity, we are all going to use Google Colab. So upper left corner here, there's a kind of the sandwich icon. You can open it, you can navigate through. So this is the table of contents. It's a long document, so sometimes you need to skip through to go to different sections. You can click the button and then you can go to that section, or you can hide it. So I'm going to go back to the beginning here. First step is to install the library. So we're going to install leaf map. So this is a Python package that I created that makes it easy for you to create interactive map and also build on top other mapping libraries, IPyLeaflet, and also MapLibre. So allows you to create 3D maps, just a couple lines of code. So we can use this to visualize some of the output or the input for the PDFM. Also, we're going to install scikit-learn. Scikit-learn is used to do machine learning. So just run the code block and then click run anyway. It should be able to install. So this might take a minute or two. And after that, we have everything set up. Then we can start executing the source code. So for this hands-on workshop, we have two sections. The first one is going to use the PDFM to predict US housing price at the zip code level. And the other one is going to also predict the housing price at the county level, but we can also visualize the data in 3D. So the first one focuses on just building the model, and then do some evaluation. For example, linear regression model and k-nearest neighbor. But you can use any other machine learning models. You can try it out. But in general, it's the for the example they're going to show you here, the R square is pretty high, so 0.7, 0.8, 0.9, and you only need a very small portion of the data for training. You can use it to do exploration or interpolation for other counties or other zip codes. Okay, so it's the installation is finished. At the bottom here, you should see there should be no error messages. And so this is a locked up space. You can click this button here to clear the selected outputs. And after that, now we can get started. So the first step is to import the libraries. Oh, by the way, so if you go to the PDFM GitHub repository, they also provide some examples. So here they have 4 examples. You're welcome to try this out. So this hands-on workshop I actually built on top of the example from here, but we only cover one scenario. You can also do super resolution, times FM, and others. Maybe we can have another workshop to introduce other use cases. But for this one, we just use the just one use case to predict the housing price. So just import the libraries. We basically import pandas to read the data, read the CSV. We also import the scikit-learn so that we can use the linear regression model and also the k-nearest neighbor regression. We're also going to import leaf map so we can plot some of the graph, the prediction and also the actual data, basically the ground truth, and also some functionality for you to download the data easily. In this workshop, we're going to use the zero housing data, but as Gautam showed that you can do a lot of other socioeconomic factors related to human dynamics. For example, median household income, health outcomes. There are a lot of things you can think about. So anything related to human behavior, you might be able to use this model to do some prediction or find some gap or missing data or something like that. So if you want to try out, for example, download the data yourself, you can click the link and then it will take you to the zero resource data. So this is all open access. You can go to the website. And so basically I downloaded the data from here. So the latest one is, you can select different levels. So for example, we're going to use the zero housing value index. It's kind of like median housing price for the entire US at different level. So because the PDFM provide embedding for county and also zip code, so you can download, for example, county. So if you select this one, again, you don't need to download it. I already download data, it's automated, but I just want to show you, if you go to get the data yourself, you can use the data that you already have, or you can Google online. And there's also Google has a data commons package that allows you to quickly get the data for zip code level or for other countries. We don't have time to cover that in this tutorial, in this workshop, but we're just going to use the data because this is already organized in a way that we can use with PDFM. So if you go click the button and you will download this one, and after that you can open this one on your computer. So for example, this is the file that if you download it directly from Gilo, so you can open it. Let me show you what it looks like. So this is the Gilo housing price file at the county level. So let me zoom in a little bit here. All right, so you have this so-called the region ID. You have the region name and the county, the state, metro, blah blah, the zip code, and also the state code FIP, and also the municipal code FIPS. And after that, you'll be this monthly data. So back to year 2000. So you can think about all the US counties has a median housing value, basically the home value. And every month you have one value all the way to 2025 here, January 31st, right? So you can see basically the trend of all the counties. You can analyze that using whatever way you want to do. But the point is that right now with PDFM, we can predict the housing price or the home value for a certain county, even if you don't have the data, right? So there will be going to be some data gap in this data set. You can feed it, or you can just select a certain county so you can predict the housing price for other counties for those you don't have. So it's monthly, every month. And for today's workshop, we're going to use, for example, the latest one, January 31st. So we want to select some counties for training, and then we can use the rest for doing the testing. Then we can compare, because this data is already pretty complete. You have data for all the counties, so you can do some accuracy assessment to evaluate how accurate is the PDFM model. Again, you're welcome to download the data yourself. So one thing I would like to point out here is we need to organize the data so that in a way that we can join the data with the PDFM, because PDFM have a column called place. Let me open this one more time here just to show you what the data look like. So sometimes you do need to reorganize the data so that they match with each other. And I'm going to show you here one more time. So this is the what the PDFM data looks like. So the most important thing is this column, the unique ID for each county, right? So it's the convention here, the geo ID. So this is the one also used in the data commons package to retrieve the data. Basically, we need to organize the data in a way that's the same as this one. So what we are doing here later is to join these two columns together. So the state code FIPS. So this one is the state ID, and then the municipal is the county ID. And we need to make 5 digits. So right now the state is just here 1 digit, some 2 digits. We need to fill in, for example, 6. It will be 06. And then the county ID will be 3 digits. So it'll be 037. So this one will be 06037. So in this way, then later we can join with this one. You also need to add the geo ID / at the beginning. So this is, once you have those, you can join together. Then we can use the PDFM features is X, basically your predictor, used for constructing the linear regression model, and the Y would be here, which column you select for the is the outcome variable, so that you can build the model and then can do the prediction. Again, we're going to use Python to automate all the stuff, but I just want to give you a big picture of how we are doing this. So basically, we have the housing price, the home value, with one column, and you have all the features, 330 features. You can add more features if you want, but we're just going to purely use the PDFM with those 330 features, and then those will be X, and the housing value will be the Y, and then you construct the model, then we can do evaluation on the model. So this is essentially what we're going to do. Again, we're going to go back to the notebook here. Now we can start executing the source code. And I also put the CSV. This one is at the zip code level, but it's similar to the county level. So I already downloaded the file and then put it on GitHub, so you can just run these 2 code blocks. It should automatically download the file to your Google Colab. So on the left side here, once you execute these 2 code blocks, click this folder icon here on the left side, and you should see this file has been downloaded to Google Colab. So this is just a temporary space. If you close the browser, everything will be gone. So make sure that if you want to save it, you can also save it to your Google Drive. You can connect your Google Drive if you want to, but you can always rerun it. It will download the file very quickly. So this is the one we're going to use. For the first one is just the zip code level. Again, it has like 30,000, over 30,000 zip codes, and it's a lot of data. So first we need to basically organize the data, and we need to basically look what's inside. So we're going to use pandas to read the file, in this zip code level, housing home value, it has the so-called region name column. So this region name, it has those 5 digits represent the zip code, right? And because the PDFM also have this zip slash format, so this line here, the second line, basically is just reading those 5 digits and then prefix it with the zip and then slash. So in that way, we have this right now. This is the unique ID for each row. So later we can join it with the PDFM because the index column are the same, so they can match with each other. So once you have that, then we can construct the data frame for doing the model. Okay, so this is what the input data from the zero housing price. So the second step is to upload to get access to the PDFM embedding. So hopefully you already have access to that after you submitted the form. And as I said, inside you should be able to find these 4 files in here. So what you need to do is to upload these files to your Google Colab. So there are 2 ways you can do that. First, you can click this button here, upload to the section storage. So if you click this one, it should pop up the dialog on your computer. Then you can go to the PDFM unzipped from here, and you can select all the files. Because we are not using the zip code GeoJSON file, it's a pretty big one, so we will use the other 3. The county GeoJSON file, basically the shape, the geometry, and also 2 embeddings. So we just need these 3 files. So just select them and click open. Click OK. Lower left corner here, you should be seeing it's uploading these 3 files. So you need to have these 3 uploaded to Google Colab so that you can read the data. Depends on internet, it might take a couple minutes. So just be patient, because if you don't have this embedding, you won't be able to do anything. But if you have uploaded, after that you can refresh it if you need it. But right now we have these 4 files. Okay, the 3 the county GeoJSON, county embeddings, and also the zip code embeddings from the PDFM embeddings that you downloaded. And the zero home value, this one is downloaded automatically to Google Colab. Okay, so once you have these 3 all the files ready, then we can start reading the file. Next, execute this one, embeddings 5 paths. So we're going to basically set a variable pointing to this one, to the zip code level embeddings. Execute the next one. So if the file doesn't exist, it's going to throw an error. So hopefully no error message. After that, then we can read the zip code embedding. So we're going to use the pandas to read the zip code embedding, and we're going to set the index as the place. So basically the embedding has the have the place column. It looks like this. So zip slash and then the 5 digits. You can see more information here. The state, the county, the city, just like the CSV they are opened earlier showing you. So those are basically the basic information about the county. And after that, you'll be the 330 features. So you can take a look if you want. Scroll from the left to the right. You should be able to see all the 330 features, basically all the weights for the model. And so now we have this home value spreadsheet with the embedding. So you can see they have these 2 columns, basically index column. They are the same, they match each other. So now we can join these 2 together so that you can have the PDFM features and also the housing price on the same spreadsheets. Then you have both X and Y. So you have the predictor variable and also the outcome variable. Then we can start building the model. So this is the line of code that you need to execute to join these 2 together. And they're going to say how basically means inner. That means if they match each other, you join them. If they don't match, then you ignore those files. Oh, by the way, I can show you like how many zip codes. For example, for the US, let me go back to the home value, the 0 data here. You can click this button to create a new code block, and then you can type len. So you can figure out how many basically GD, HF, DF. You can see how many zip codes in the 0 housing data. So this is 26,322 26,323 zip codes. Let's look at how many in the PDFM. So same thing here. We can create a new code block and then just type len zip code embeddings and then run it. So for the zip code embedding, we have 32,069. So basically the PDFM zip code embedding has a lot more than the US, the zero data. It makes sense because I mean in the US we have over 40,000 like zip codes. It's a lot more than what we have here. But for in terms of housing, there might be some places that don't really have enough population, so zero doesn't collect the data. So just though to keep in mind, so 26,000 compared to 32,000. But when you join them together, you might end up with less because we are using the so-called inner. So if I run this code block, now we have this new data frame with the two data sets joined together, but we also have this index column. That's basically where they match each other. And so we will have this one, 2000, basically the housing value data here. And there you can see the three dots because there are too many columns, so it doesn't show up. But it should be 2000 January 31st to 2025 January 31st. So you have monthly for 25 years of housing, medium housing price for the US at the zip code level. And then we also have 332 features from the PDFM on the right here. So you have a huge data table. Now we can use this one to do some machine learning. But as I mentioned, let's check how many rows in there. So I want to show you maybe the length data. So you can see right now we have 24,000. So 26,000, 32,000, and now we end up with 24,000. So basically a little bit less than the median, the zero housing data. So, but it's still a pretty big data set with 24,000 rows and with over 300 columns of data. If we save this one to a computer, it's probably a couple hundred megabyte. Okay, so once we have that, now we can start prepare the data for the model. So how we're going to do that? Because if you want to build a model, you need to prepare the X, basically the predictor variable and also the outcome variables. So in this case, the predictor variable will be just the PDFM features, right? So you can use this one, the feature for starting from 0 all the way to 329, right? So 330 features. And the Y for the label, we're going to use January 31st, 2025. Again, it's in the spreadsheet if you want to see this one. So we're going to use this column all the way to the right here. You'll be this column. So this is what we are trying to predict. Okay, so this is the median housing price at the zip code level for the entire US. So this number, for example, the first one is 880,000 US dollar for that zip code level. And the X would be this embedding. So not including this, okay? So these are ignored because these are just the basic information is irrelevant to the model. The model already captured, the PDFM embedding already captured the spatial relationship between those zip code labels. So we don't need to include this one in the model. What we need is from feature 0 all the way to features 329. So basically 330 features for the predictor. And this is what essentially what we are trying to do here is to get those column names. And once you have that, we can also drop the data. So if there's any no data, for example, in the label, if there's that zip code doesn't have housing value, we can drop it. But you don't necessarily have to. So PDFM can actually fill in the no data, but in this case, just to make things seems easy, because later we're going to compare the prediction with the ground truth. So if you need to do a comparison, you do need to have the data, but you can certainly use that to fill in the no data. If your goal is to, if for example, some zip code that you're interested in, 0 doesn't have the data for that, you can later use PDFM. Once you build a model, you can use the feature to predict the housing price for the zip code level. So we can drop all the no data. And now if you want, you can take a look, see how many are left. So I'm going to run this one again. It's the same. So basically you still end up with 24,000 zip code, 24,000 lines of housing price and also the PDF embedding. Once you have the data ready, now we are really getting into building the model. And like I said, you can use very complicated deep learning models, or you can just use a simple basic regression model. Before we fit into the model, we need to basically split as training and also testing. So in this case, we have this pandas data frame. So basically we have the 330 features and also the label, the housing value for January 31st. And the X would be selecting the 330 columns, and the Y would be just selecting the January 2025 January 31st. So this would be the X, basically it's the matrix, and the Y would be the outcome variables. Then we can use the scikit-learn strength test split. So you put in the X, put in the Y, and the test size is 0.2. Even to learn more about the parameters, you can hover your mouse here to be able to see all the parameters available for all the functions. If you want, you can scroll down, you can see more information. So the test size is, excuse me, is 0.2. That means we're going to use 20% of the data for doing the testing. So what this one essentially is doing, we have 24,000 rows. So we're going to use 80% of those for the training the model, and we're going to use the remaining 20% for doing the testing. But you can adjust the number. I will show you how to adjust it later. And the PDFM embedding is pretty powerful because you actually don't need 80%. You can use 20% for training. You can then use 80% for testing. It still give you pretty good results. So right now, let's just use 80% training, 20% testing. Then we can see this, okay? So you can see right now we have this data organized in a way that we can make it ready for the model. So this training data, the X would be these 330 features, and the Y would be just the column, the housing value. If you want, you can double check that. So for example, len X train, just to see how many rows, right? So this is 19,202 rows. And for the test, you can also run it, len, lowercase, and then it will be Y test 4,801, right? So it's 80-20% split. Once you have the data, now we can fit the model. We're going to use the scikit-learn linear regression model. As I mentioned, you can use other deep learning model as well if you want to, but the simple linear regression works pretty well. So once you have the model constructed, then we can fit the model. All we need is just passing the X and Y, right? So your X, basically your predictor, and Y is your outcome variables, values. And once you fit the model, then you can do the prediction for the testing, right? So we fit the data, fit the model to 80% of the housing value data and also the PDFM. Then we predict the rest of the remaining 20%. So we're going to end up with a vector here, the prediction. So this will be the prediction, but we also, because the data have the ground truth, so we can compare these two. Then we can call this function. We can construct the data frame. So let me show you here. You can see you can already calculate the matrix, but let me also create a new call box, show you what this one looks like. So the evaluation data frame. Okay. So this one just shows you like the data frame. The Y means is the data coming from the 0 data set. The Y predict basically is what the PDFM predicts, and you can compare the differences here. Overall, they're not going to be perfect. I mean, there's going to be overestimated and also underestimated. But if you look at the matrix, so the evaluate model, so this is the a function from leaf map that makes it easy for you to compare two columns. So the R square is 0.77. That means the PDFM prediction can explain roughly 77% of the variation, and the correlation coefficient is 0.87. So that means the X and Y, they align pretty well. This is a decent correlation coefficient. R squared means basically this one take the square, then you get 0.77. Also, you have the root mean square. MAE is the mean absolute error. MAPE is basically the mean absolute percentage error. So those are basically some of the common matrices used to evaluate machine learning models. Basically, you have two columns, and how do you figure out whether they match, how well do they match each other? So the value here, the R, means it can range from, for example, -1 to 1. So you can have negative correlation, or you can have positive correlation. So in this case, we certainly want a positive correlation. Ideally, we want the R to be 1, right? So basically the Y, the ground truth and the prediction are exactly the same, but it's not going to happen in cases like this, because it's not going to be a perfect model. But in terms of the R square, it's pretty high, 0.77. So this is just a matrix, but how about we plot that in a graph so that you can easily see what it looks like? And because there are some like very high values, housing price, there are also some like low, some very extreme. But we can use this one simple line function from leaf map, plot actual vs predicted. And we're going to use this evaluation DF, basically this data frame here with almost, I think, 4,801 rows. Then you can set the X limit. Basically, we're going to set the limit as, or the XY limit. So the I'm going to say from 0 to 3 million, right? So this will be the actual value, the horizontal axis. It will be the 0 median home value, and the Y will be the PDFM prediction. As you can see, it aligns pretty well. Most of the points, most of the US housing, I mean, the median housing price is smaller than 1 billion, 1 million, 1 million here, 1.5 all the way to 3 million, but there are some other like tens of millions. Those are more like very extreme use cases. Values, you can click your mouse, you can zoom in, you can see the data here. So you can see the point. So what we want is to have the prediction align with this diagonal line 1 to 1. So that means the ground truth and the prediction are very close. But this is where at least you can see, right? There's a trend line here, and it's a positive correlation looking at like this. And you can have your mouse, you can see a particular point, for example. You can see how much they vary. The more you deviate from the diagonal line, that means the worse the prediction. And so this is just the PDM, right? We don't need any additional data. We all need just the PDFM, and then give me a column of housing value for zip code, and then I can do the prediction for others. You don't really spend time to figure out like what's the outcome variable, because you can build a complicated model, but you need to collect the data, you need to do all kind of things. So this is the power of using foundation model. That means you don't need to train your own model. You just use the embedding that's already captured the spatial and some of those relationships because it's aggregated from the maps data, the search, and also some of the local variables. There are a lot of things already in here, but it's hidden. It's so-called the embedding. Basically, it's just a numerical representation that captures something. We don't know what exactly it is. Just like using large language model, or Gemini, ChatGPT, whatever. You enter some text, you're going to spit some results. In this case, it's the same thing here. We give the model some housing values, is going to give you some other housing values for other area you want to predict. So this is essentially how we can use the model to do prediction. And yeah, that's pretty much it. And you can see, besides the linear regression model, you can also use the k nearest neighbor model. There's the same step. You can set how many the k here, and then after that, construct the model. Then you fit the model, and then you do the prediction. So you can run this one. After that, you can evaluate the model. Exactly the same, just like what we did using a linear regression model. So this one is slightly lower than the previous one, 0.77 here. And then ask the correlation coefficient is 0.878. This one is 0.88. So very much, very close. And this is how you can use. As I mentioned, you can adjust the training split. So let me go back to the model here. Earlier we used 0.2, 20% for testing, but you can change it, for example, to 0.5. So we have 24,000 zip codes. I can just use half of those for training, and then use half of those for prediction. So let's see how it's going to perform. So let's run this again. And let me run the model. Okay, so remember this is initially is 0.77 and then 0.87. So let's run this model again. Okay, did I fit the model? Oh, I probably need to split the train head and run this one again. Fit the model, run the model. It's still pretty much the same. Here. So did I make something wrong? Train split. Let me change to maybe 0.8. So that means we use 20% for training and then 80% for training, 20%, sorry, 20% for training, 80% for testing, and see if the accuracy changes. You see? So right now we're only using 20%, just a tiny portion, and it still has a very decent correlation coefficient. So 86.86 with R square of 0.74. And it's amazing, right? So you can use a tiny percent for training. You still get a very good model outcome. You want to get a lot more points because we have 80%. So this one is 80% of that 24,000. It's a lot of zip codes. If you zoom in, it's going to take a little bit longer. So you can see how powerful it is that with a limited amount of data, you can do prediction pretty well. So this is how you can use the PDFM to do like prediction on the US housing price at the zip code level, very fine detail. Next, I'm going to quickly show you some of the applications. This one will use the county level data, but we're going to want to use some map because we want to visualize the data. Because right now the notebook has been run for a while, so it becomes a little bit slow. I can restart the section so I can clear some of the outputs. And then I can go back to the second section here. We can start importing the library. So the next one, we're going to map the PDFM features because right now you have the spreadsheet with 330 features. We don't know what it is. It's just kind of like a black box. It's not a black box. It's just numerical representations. But we don't really know what each number represents. But there are some relationship at least. Spatially, we can visualize that. So we're going to import the data and download the US county level housing price data. And the same step, we're going to basically process the data so they organize in a way that we can join with the PDFM. So I'm going to go to here. But in this one, because we are going to map them, we need to use the county GeoJSON from the PDFM. So basically the county GeoJSON file has the column, basically all the geometry. So we can join them two together. So let me click this one. To load the county boundary. So the county also have this column indicate the ID. We also have the geometry. Once we have that, now we can join these two columns. So we're going to join the US housing price data to the geometry, to the map, to the GeoJSON, because the CSV doesn't have the geometry and the GeoJSON file has the geometry. So now we join the data together. So in that way, now the housing price can be plot on the map. Also, we're just going to select one column because this the housing price has like monthly. We don't need all of them. We just want to look at January 31st. So now we have this vector data with the ID for each county. We also have the vector. With that, now we can just create a map to visualize that. So if you want this one, it will take a couple seconds to create a map and load the data. My lights off. So here we're using leaf map, and so leaf map can load, visualize any vector data set, and you can have just provide the geodata frame. You can provide a color, and after that you're going to create a map. So this is a little bit slow. So if you can install packages on computer. It's going to be a lot more responsive because it's still a pretty large data set. So I'm going to show you here on my local computer. Oops. I probably already closed it, but let me show you here. Open my file. And 1 second. Yeah, okay, it's already shows up. So again, this is to the map. So this will be the housing price for January 31st, right? So you can look at where the darker color represent higher median housing price. That lighter color means like lower. Low right corner here, you can also see the value. So the darker one. So this is using the quantile classification scheme. So basically means we have 5 categories, and each category represents roughly the same number of counties. So basically it spreads out. Otherwise, you're going to have some extreme values. The map is going to look just very little bit distorted, because most of them you might have like 2 extremes. But if you want, you can change the classification scheme to others. You can hover a mouse, you will see all the parameters for the function. If you scroll down, there's a scheme here, classification scheme, right? You can use a quantile, you can use a equal interval, kind of similar to the desktop GIS. If you're already familiar with GIS, you can change this one, just the scheme variable change to others, then you can change how the map looks like. So this is what the map looks like. You can zoom in and can zoom out. But it'd be nice to see that in 3D, because if you want to see the data, how it looks like, this is so much better in 3D. Again, it's going to take some time. I'm going to show you here on my computer. It's going to be look much better. So here, all right, let me zoom in a little bit here just to show you the 3D. And if you run your local computer, it should load up very quickly, right? So this will be what the data looks like, the 3D map here. The same thing. Again, it's going to take a couple seconds to load up, but I'm going to show you, right? This will be the 3D map, and you can zoom in here just to show you. So this is the original median housing price for the US at the county level. If you press Control on your keyboard, you can zoom in and zoom out. So basically, you just like a couple lines of code, you can look at the data. And this shows you clearly like which US county has higher housing price, which US county have low. You can see clearly like these are some of the extreme counties. And you might be surprised, like some here in the US Midwest, like have very high housing price. But of course, California is known for its high housing price. New York, right? So you can click your mouse, you should be able to see the state and the county. So this is Massachusetts. And also lower left corner here, this would be, I think, Miami or somewhere. The county where those big cities. I can also take a look at where, for example, my county here in Knoxville, Tennessee. It's click my mouse. It's 356,000 like median housing income. No housing price, right? And let's look at here. What's the one like really extreme? Is this maybe this one? Okay, Teton County, Wyoming, right? So this one, the median home price is 2 million, over 2 million. It's crazy. So those are basically tourist counties that people like maybe have vacation homes or something like that over there. Again, you're welcome to explore. If you're using Google Colab, it's a little bit laggy because the widget support is not very well, but you can right click your mouse, right click, and then you can drag and drop something like this. And then you can zoom in using your mouse, the wheel to zoom in and zoom out. But try not to click other stuff. You will end up like this. Localhost refuse to connect. Okay. It happens. If it happens, then you click run again. Exchange the map. You just need to be careful because Google Chrome doesn't support this kind of a iPad third-party widget very well. So for base experiences, you might want to install those on your computer, and it's super smooth. Okay, so this is just mapping the original housing data. Now let's look at the embedding. So I'm gonna go quickly because we only have 10 minutes. So right now we're gonna load the county embeddings, and we can also join the county embedding to the GeoJSON. Again, the embedding just the CSV. So we join to the GeoJSON. So in that way, we can have all the data, we can visualize them. So after that, we're going to visualize the PDFM. So PDFM has 330 features. You can change this one to whatever feature you know visualize. And then we're gonna construct this geodata frame. So in a way that we have the geometry, we also know the state and the county, and then we look at that particular column of the feature. So this is the last PDFM embedding, the last feature, and let's look at what it looks like. So again, I'm going to create a map, and it looks like this. And this is not housing price, okay? This is just the PDFM feature. As I mentioned earlier, it's just a numeric, it's just a weight, it's just a numerical representation capturing something. based on the aggregation data from maps and search and all those data PDFM utilize. I don't know what it is, but you can guess, right? You can look through the 330 features. I don't know, it's going to change. So in this one, it looks like they have some cluster here, high value, have some low value. Again, it's just like a black box. If I change it to something else, maybe a feature 100, it's going to look totally different. So each feature captures something, although we don't know what it is. It's something. So zoom in again. Now it looks like this. California is always high, always darker color. It's very strong. I mean, on the map representation, but other parts kind of a lighter color. So you can see also from here. You can click your mouse. You can look at the value, which county, what's the value, and so similarly, I can find maybe my county here, for example, Knoxville, Tennessee. If I click this one, it's the feature value is 2.35. I don't know what it is. It's something. So there you can actually go through the 300 feature. You can maybe do some machine learning, or you can do some reduction of those maybe principal component analysis or something. You can try to distill some information from the embeddings to figure out like what does each feature represent. Right now, there's no meaning. So each feature is some information, is some weight, but you can also visualize them in 3D. So similarly here, I can create a map and then just load the PDFM feature, and it looks like this. And so now you have this, right? So again, this just show you something here. If you don't like the color, you can change the color to whatever color you like. So for example, I can change to cool, warm. So you can use any map, any matplotlib color map. So you can change it easy, something like this. So cool, warm, blue, red, yellow. It's very, very flexible. So now you can clearly see, for example, blue color represent low value, red color represent higher value. So once you have this, now also this one extrude means you want to use the 3D. Also, when you have the scale variable, because when you represent like render this data in 3D, it's going to use the elevation because and the elevation only ranges from 0 to 8,000 roughly. So because the housing value is like hundreds of thousands or to millions, so you need to have a scale factor to scale down the value. You can change it. So for example, if you change it to maybe this, the bar is going to be much higher. So everything you can make some adjustments, something like this. Okay, so this is the PDFM feature, and so next let's quickly run some models, and so I'm going to do the same thing using the January 31st as the outcome variable, and then we're going to join these two data together. Then we're going to do some predictions. So I'm going to quickly show you the same step as the previous example using the linear regression model. So for this one, take a look. We have R of 0.91. So means right now we use the county level with roughly 3,000 US counties, and we're going to use 80% for training, 20% for testing. And look at the matrix. It's pretty good, like 0.91. It's very impressive. Again, we don't need to build your model. You don't need other variable. You just use the PDFM. And this is what it looks like. Similarly, you can visualize the data. So now with this, we can visualize the data, join the prediction to the county boundary so that we can see what's the actual home values. So I'm going to show you this one here. This will be the 20% for the testing. So 20% of the US counties. So this will be the data coming from 0, okay? So the median home values. And then we can also visualize the prediction. So this will be the PDFM predictions of those 20% of the US housing price. And you can see, you can compare these two side by side if you want to, but you can just do the subtraction. So we just see the differences because with the evaluation, we can have those two columns. So now we can actually see the differences. So this will be the last map they're going to create here. So basically the PDFM prediction minus the ground truth from the 0. And so if this blue color, it means the PDFM underestimated the home value. If this red color, it means the PDFM overestimated the value. Although right now it's kind of very spread it out because we only use 20% of the counties. But like I said, you're welcome to change it. So let me do something like what we did earlier. Similarly, I'm going to change maybe to 80% for training. 20% for training, 80% for testing, see how it works, right? So remember this one, 0.82 and 0.91, and let's see how it works. So right now, we only use 20% for training and see how it works. Okay, it's Gex mass was the R square is 0.52, and this one is 0.78. Probably it's too much, maybe 0.5. Because we don't have that many US counties compared to the zip code. Okay, so this one's still pretty decent. Half for training, half for testing. And the correlation coefficient is 0.89 and R square is 0.79, 0.779. It's still pretty good. So take a look, right? That means if you need to predict a US county, right, the home price, you can use the PDFM and just feed in some existing data and then do the prediction. It can be housing price, it can be median household income, it can be anything related to population dynamics. So once you have that, just run the model again, and you can visualize the data. Now you should see a lot more counties. So this is half of the US counties. This would be the ground truth from the home value, and this would be the prediction from the PDFM. And lastly, we can visualize the changes, basically the differences between the prediction and the ground truth. And now you have a lot more data. Again, the blue represent underestimated, the red represent overestimation. So for example, you estimate much higher for the Miami here, this county. And yeah, so you can explore it and adapt the source code to some other data. All you need is basically just prepare the data, whatever variable that you're investigating, then you only need just to have that Y, basically your outcome variable. Then you can just use the PDFM, whatever features, 330 features to fit into the model. You can also export it. Let's say you only use 10% of the PDFM features to do the prediction to see how it performs. Sometimes you might not need 330 features, although you have a lot of features, but you may not need all of them because for some variables, certain features might already capture that relationship. So in that way, you don't need that many because the model, your regression model will be pretty long. So, but I just show you some of the potentials, how you can use this for the US county level and the zip code level. When I have time, I should maybe create another notebook showing you how to do super resolution. For example, assume right now, Zero doesn't release median housing price for zip codes. They only provide the county. What I can do is to use the county to build the model, and then I can use the PDFM to predict the housing price for the zip code for the entire US. And it's still probably going to give you pretty decent result. Although you don't have data at the zip code level, but you can do the super resolution to increase that. So maybe you have some medium housing price or house income or health outcome, education level, those kind of things. It's up to your imagination what you want to do, but hopefully this is something useful for you to get started and adapt the source code and try it out, see how it works. We're happy to hear your use cases. You're also welcome to reach out to the PDFM team to show them what kind of things you have done and how useful it is for your use cases. Okay, so that's all I want to present. If you have any questions, happy to address questions. And David and also Gautam, they are here. They are the contributors to the PDFM, so they know a lot more. I mean, in terms of the theory and the foundation of the models. I'm just an end user, and my goal is to make it easier for other users to utilize this kind of state-of-the-art foundation models. Thank you very much.
Thank you so much, Kisheng. This is incredible. I was going step by step as you were showing and just blown away on how simple it is to follow and run this with Google Colab. It's very impressive. I'm looking forward to the future tutorials myself, and I'm sure our audience have a few questions. Perhaps I could call on Maria to start us with a few questions from the audience, and I have a couple of questions myself if we have time later.
Yes, thank you, Kisheng. Thank you, Rainy. And yes, there is already one question from the floor, and then I have also a question, but let us see because we have only 9 minutes. Anyway, first question is from Marvy McCutcheon. I hope that the pronunciation is good. How well do PDFM zip code level embeddings perform at higher resolution, such as parcel level? You partially already answered. Have you explored combining multiple zip code embeddings to represent a single parcels and assess their effectiveness? I don't know who wants to answer, if you, Qiusheng, or
yeah, right now the embedding only have county and zip code level. They don't really have the parcel level. Again, earlier in the introduction, David also mentioned about some of the privacy issues. So it's more like aggregation. You don't want to go to too details, then you can like have a lot of privacy concerns. And right now, I don't think you can do super resolution to the parcel level yet. Maybe in the future. Right now, the answer is no. David and Gautam, they can provide more insights. So county and zip code level is only the embedding that we have right now.
Okay, thank you. Then, Rohini, I see that there is another question from the floor if you want to ask.
Sure. We have one from Kunshan. So Kunshan has a question on the application side. As embedding usually consists hundreds of features, would you recommend for a very limited scenario when the research area is a small county, let's say 20 admin units, so only 20 values is ground truth that you have?
Yeah, good question. So basically for this kind of model, you do need like enough data to train the model. And I'm not sure you are talking about county or country. For country right now, they have not released embedding for other country yet. Right now, it's only limited to the US counties and also zip code level. If you only have 20, it's going to be tough. I'm not quite sure. You can try out, actually, you can try out using the notebook that I provided for you. You can just randomly select 20 counties and you see how it performs. It depends, right? So think about here, if the county that you selected are pretty like normal distribution, like only have couple extreme values, but majority of them is like pretty normal distribution, I think the model is still going to give you good results. But most models are going to have a hard time trying to predict outliers, right? And just like COVID, I think none of the health models in the past would predict COVID to have such a large impact, right? So those are more like a very outliers in history. Same thing in here. If your model happen to select, for example, the Teton County that I showed you earlier, right? The median housing price is like over 2 million. Who can actually predict that? Because the surroundings are pretty slow. So it depends on the data, depends on the distribution of the data. If you only have a limited number of data points, then it's going to vary a lot. Depends on how many outliers in your data set. You can only do what you have, right? Sometimes data is going to be an issue for this kind of AI applications.
Okay, thank you, thank you. And I have a question, I believe, for David or Gautam, as a matter of fact, because I want to understand which are the competitors of this model. Is the unique population dynamic model, condition model, or are there other examples?
I can take that. I'm unable to turn on my camera. If someone can do that for me. I mean, the data, ultimately, the data that feeds into the embeddings is what makes them unique. And, you know, search trends and maps mobility data is such a unique data source that we very much sort of see it as something you would add to the data you've got, right? So it's an additional covariate, but it is a very unique data source. So that's why we've been really sort of trying to see how can we make it available, but without sort of disclosing the sort of privacy issues that concern individuals.
Okay, thank you.
Also,
Yeah, I can also chime in. Gautam, go ahead.
Yeah, well, like even in like we studied combining it with SatClip, which is another embedding based on satellite data. And if you look at both of them, I think it's on elevation. They perform equally, but if you combine them with the PDFM and SatClip into like one model, we can further push performance. So oftentimes, like, we can just provide value if you have other geospatial embeddings and combine them with like sort of the specific data that's available in PDFM.
Yeah, I can also like chime in a little bit that I think the power of this is that the embedding already captures it. You don't need to build a specific model, right? So traditionally, if you're trying to predict the housing price, you need population in that county, you need maybe the income level, education level, all kind of different variables trying to collect the data and then to build the model yourself. Because it's right now it's your foundation model, you already have those embeddings, so you don't need all those data. So you only need to just fit in your Y. You don't have to worry about your X, your predictive variables, and this makes things really easy that you can apply to so many scenarios, not just for housing price. It can be like a lot of those examples that Gautam in the slides, that there's so many potentials. Like anything related to population, relates to human, somehow it's already being captured in the embeddings. And some might be very strong, some might be weak, but user can try out and see how it performs. Of course, if you're trying to maybe, I think this is very similar to the computer vision, right? We have a lot of dedicated model for doing specific things. For example, building detection. You can train a model just to do building detection. It's going to be very accurate. But if you're trying to have some segmentation model, there's I mean, the segmentation model is going to be, in general, is pretty good. You can give me something, I give you the segmentation, right? Although it's not going to be as high, the accuracy as high as a particular specific model. I think it's very much similar here in the PDFM, but it's in the, like, this guy's human dynamic context that you don't need to train those. You just use the model and then you can do the prediction and see how it performs. If you have the data, you're welcome to train your own dedicated models. You can also add more features to the PDFM embedding, right? In addition to those 330 features, you can add more, or you can just select some features from PDFM. You can add your own data and then you can do the prediction. So there are many ways we can, like, I mean, utilize these embeddings to do machine learning.
I think what's interesting about it is that what you have is something that characterizes the location, the resolution of the individual, geos for which you've got the embeddings. And one of the open questions, I think, is what happens as you increase the data sources that go into creating that embedding, right? It more and more uniquely defines the location, but what is the utility of that? And I think that's just a fascinating question to sort of explore.
Thank you so much. Just one last question from my end. What would it take to get something similar for the rest of the world? Is this something in the plans for PDFM to provide embeddings for other places?
Yeah, we are actually working on it. We're working on a handful of countries right now, mostly right now English-speaking countries, just for the sort of transferability of search profiles. But then we are looking. The thing that is important is that the data sources we're putting in, we need to make sure there's enough data coverage. And so where you've got high internet penetration and high usage of search and maps, we have quite good data. So any country where that is the case, then that's obviously we can generate. And we're looking and sort of thinking about, in those sort of geographies where that's not the case, then what is a good alternative. And I'll just mention it. I came across a project called GDELT, which is looking at putting together a sort of global footprint of news and possibly social media, which I think could be a wonderful source for sort of completing that footprint. And then you sort of start to look into questions of how do you deal with different degrees of data sparseness in the embeddings and incomplete data that goes into it. And what do you just sort of say that there need to be different embedding sets for different sort of strengths of input signals, and I think that's part of the open research as well. But anyone that's actually interested in other countries, would just love to hear your use cases and also the countries, because it helps us prioritize the work. And so, yeah, hopefully things will be sort of, we can make them available.
Thank you, David. And we have 2 more questions. So I will ask the first one, really the second, and then I believe that we will close. So the question is a question from Matt Cooneyholm. Is it possible to use these for future scenario predictions? I don't know who wants to answer.
Yeah, the answer is yes. It's actually they have a notebook in the GitHub repository for using the Times FM. We don't have time to get into details for that, but you can utilize that notebook and then you can do forecasting for using the Time FM and also the PDFM embeddings.
Yeah, I'll also add, that's absolutely right. You get into some sort of interesting questions about temporal dynamics of places, right? And so if a place's characteristic doesn't change much over time, then the embeddings that we released, the experimental embeddings we released, are actually pretty good representation. But if you're looking at a place which has a very fast-moving temporal process, let's say that like imagine somewhere hit by wildfire like LA or something like that, then perhaps the embeddings will be drifting relative to the reality on the ground. So we are actively looking at how we could create sort of temporally aligned, if you like, embeddings over time. But it is sort of this question of how fast moving are the processings that the embeddings are trying to model.
Thank you, David. One last question from Matthew Lim, and this crossed my mind as well. Qisheng, this is probably for you. Can we use the same zip code or county embeddings we used for this workshop and change the Y output variables to train the data for different use cases?
Yeah, of course. Yeah, that's the whole point. Like you can do median housing income, you do education, you get health outcome. You can look at the paper. They have run their own like so many different use cases. So as long as the data at the zip code and county level, your Y can be pretty much anything. Just use your imagination, whatever you use, anything related to something like human population, or even can be environment, right? The elevation or things like vegetation, whatever. You can try it out. The embedding capture like a variety of things. So you can change the Y to whatever you want, and then see how the model performs.
I believe that this is answering also the last question, which is, can we use it for census data? Because we said that you can use for everything related to.
Yeah, census data have like different level, right? County, state level, county level, zip code level. But you may not go all the way to like census check level because it's aggregated. But in terms of county and zip code level, and the census data have so many those variables, you can use it like to do training to prediction. And so this will be like, for the census data, right? We need like every 10 years. And with Google, this kind of PDFM, for some counties, that if you happen to don't have data, or you want to quickly, for example, predict next year or next 5 years, you might be able to use Times FM and also PDFM just to predict based on the source data. For example, what's the population? What's the migration chain? For example, what's the income flow? For example, to Florida, and with all this socioeconomic data, and you can predict the economic status of a certain county, a certain neighborhood. Utilize some census updated data, but because the data takes time to have that, for example, every 10 years. So they do that maybe this year for this county, this year for that county. Then you can use the model to do prediction. You don't need to wait until the official data have been released. You can predict that. Or you can maybe, for example, the Federal Reserve, release laws like economic data, although it's not at the county or at the zip code level. But I'm just saying, if there's certain things that you're interested in is not available, then you may be able to use the PDFM to do predictions at the county and zip code level. If you already have the zip code level, it's already pretty detailed, right? We have over 30,000. So there are already a lot of things you can do with the PDFM.
And I'll add, I think this is Marvin's question. You can aggregate a zip code to cities or whatever administrative region you care about. We've done experiments with that, and that works pretty well too. So you're not restricted to just county level. Anything that you can aggregate zip codes with.
Yeah, that's awesome because, for example, the Gilo, right? They have metro area, city, and also like zip code, and then yeah, those would be nice to have. Yeah, so they in that way cover a variety of different spatial scale.
Okay, so thank you so much to all of you, all the speakers. It was a very exciting presentation, so thank you, and I encourage everyone now to try to use it. And I give the word to Rohini. Rohini, do you want to close this wonderful event?
Thank you, Maria. And I agree with you. I feel like the future is already here. Thank you so much, Kisheng, David, and Gautam for this great webinar and workshop. And Maria, thank you also to you for moderating this event together. And the big thanks goes to all our participants. We're sure you learned new skills in this workshop, as we also surely did, myself for sure. The workshop material is available in the neural network, and of course, you can watch the recordings in the YouTube later as well. I also want to remind you that in March, we will have 2 workshops organized by NASA and IBM on a different geospatial foundation model. On 19th of March, we have an Earth Observation Foundation model with Prithvi, Earth Observation 2.0, and Terra Torch. And 26th of March, we have one on weather and climate. So stay tuned for those exciting developments in GeoAI and geospatial foundation models. And I thank all of you once again for your participation. With this, let me give it back to Anna.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.